Okay, welcome back. Now, what I want to look at today is magnetism. And looking at magnetism, I'm going to do a video as well. Now, so in regards to this session, you will need to be looking at magnetism in respect of the video. So you will need to bear with me, okay? Now, so I just make sure that I can hear the microphone is not covered over. Okay. Now, go here for a second. And crumpet. Crumpet. Okay. The main thing is to make sure that got everything in line up. Yeah, good. Okay. What I'm looking at. Okay, good. Well, what I want to look at today is magnetism. One of the first composites of fish-shaped iron leaf was mentioned in the Wu Ching Sung Yao, written in 1040. Okay, and this is not me who's saying this, but this is from a guy at Trinity. Now, animal magnetism. Now, we all like to think we have magnetism when we go out on the night and we're at a nightclub and we are trying to attract the girls. And so we're looking for our animal magnetism and we try to put on our best charms. And then you go up to this girl and you begin to talk to her and you're thinking you're sounding good. She looks at you and simply swipes left. Now, that's the thing these days, isn't it? Swiping left. Leave me alone, go away, basically. Okay, but fortunately, that's not always the case. Okay, so here we have animal magnetism. A frog suspended in an intense magnetic field. All of us are paramagnetic. Much money is wasted on magnetic therapy. Okay, I have no idea why anyone wants to spend money on magnetic therapy. We are magnets in our own rights. Here we have. That's interesting. Sorry. Okay, that's okay. Here we have magnetic attraction. They also attract other magnets. Okay. Magnet attracts magnetic materials. Okay, that's what that's trying to say. Now, it is possible to produce motion using magnetic attraction and or repulsion, either permanent magnets or electromagnets, or both can be used. Okay. Now, magnetic attraction and repulsion. Opposite poles attract, like poles repel. Of course, one of the many facts we all recall from our earlier science education in school. But how do we make this work for us in a way that becomes productive, that becomes energetic, that gives us electricity, that gives us a motor car, for instance, that enables us to recharge the batteries in our cars? Okay, I mean, so we're looking here at DC motors. The stator is the stationary outside part of a motor. The rotor is the inner part which rotates. In the motor animation, red represents a magnet or winding with a north polarization, while green represents a magnet or winding with a south polarization. Opposite red and green polarities attract. Now again, still on DC motors, just as the rotor reaches alignment, the brushes move across the commutator contacts and energize the next winding. In the animation, the commutator contacts are brown and the brushes are dark gray. A yellow spark shows when the brushes switch to the next winding. And you can see that the brushes switches to the next winding simply because of a gap between that. So it bridges the gap and retains the motion in play. DC motor application now: automobiles, windshield wipers, door locks, window lifts, antenna retractors, seat adjust, mirror adjustment, anti-lock braking system, etc., etc. It goes on and on. And the list has become even more wider and extensive. Cordless hand drill, electric lawnmower, fans, toys, electric toothbrush, servo motors, etc. Okay? And those are DC motor applications. And I'm sure we can find even more now than ever before. So don't be limited just by what you see here. Bear in mind that there are now an extensive range of motors, especially with some of the work that they may be doing in outer space. Maybe we will get free space motors. Big man's motor. Now, a simple DC motor made with a battery, two paper clips, a rubber band, and about 1 meter of enamel wire. Okay, and that's all it is. Now, brushless DC motors, I should say, brushless DC motors. A brushless DC motor has a rotor with permanent magnet and a stator with windings. So here you have your stator with windings, and here you have a permanent magnet. It is essentially a DC motor turned inside out. The control electronics replace the function of the commutator and energize the proper windings accordingly. Okay. Now brushless DC motor application: medical, centrifuge, autos, otoscopic surgical tools, respirators, dental surgical tools, and organ transplant pumps, etc., etc. Okay. Now, full stepper motor. Okay. This animation demonstrates the principle for a stepper motor using full step commutation. The rotor of a permanent magnet stepper motor consists of permanent magnets, and the stator has two pairs of windings. Just as the rotor aligns with one of the stator poles, the second phase is energized. The two phases alternate on and off, and also reverse polarity. There are four steps. One phase lags the other phase by one step. This is equivalent to 1/4 of an electrical cycle, or 90 degrees. And here we have the half stepper motor. Okay. This animation shows the stepping pattern for a stepper motor. The commutation sequence for a stepper motor has 8 steps instead of 4. The main difference is that the second phase is turned on before the first phase is turned off. Thus, sometimes both phases are energized at the same time. During the half steps, the rotor is held in between the two full step positions. A half step motor has twice the resolution of a full step motor. It is very popular for this reason. Has twice the resolution. Yes, yes, that's what I said, I think. Okay, let me just step back. Okay. Now, stepper motors. This stepper motor is very simplified. The rotor of a real stepper motor usually has many poles. The animation has only 10 poles. However, the animation has only 10 poles. However, a real stepper motor might have 100. These are formed using a single magnet mounted in line with the rotor axis and two pole pieces with many teeth. The teeth are staggered to produce many poles. The stator poles of a rail stepper motor also has many teeth. The teeth are arranged so that the two phases are still 90 degrees out of phase. This stepper motor uses permanent magnets. Some stepper motors do not have magnets and instead use the basic principle of a switch reluctance motor. The stator is similar, but the rotor is composed of a iron laminates. Okay. More on stepper motors. And here we have the rotation. Okay. I'm simply showing you the cycle as to what's happening. Okay. Let me pan back a bit, make sure we can get this in fully. Okay. So you will need to be able to see and relate to this yourselves. So let me go in close and then pan back so we can get it fully in. Now note how the phases are driven so that the rotor takes half steps. These are your controlling device to the stepper motor, okay? More on stepper motors again, still. Animation shows how coils are energized for full steps, okay? You can see the switches here opening and closing accordingly, which produces your supply and causes the coils to be energized. Okay? Around the poles. You guys make sure that you're going to look at this, okay? Magnetism, okay? And brushless AC motor, okay? Now, a brushless AC motor is driven with AC sine wave voltages. The permanent magnet rotor rotates synchronous to the rotating magnetic field. The rotating magnetic field is illustrated using a red and green gradient. An actual simulation of the magnetic field would show a far more complex magnetic field. Okay, but this is just simplified for our own benefit. Okay. Let's make sure we can listen view. Okay. The AC induction motor. Now, the stator winding of an AC induction motor are distributed around the stator to produce a roughly sinusoidal distribution. When three-phase AC voltages are applied to the stator windings, a rotating magnetic field is produced. The rotor of an induction motor also consists of windings, or more often a copper squirrel cage embedded within iron laminates. Only the iron laminates are shown. An electric current is induced in the rotor bars, which also produce a magnetic field, which causes one field to push against the other, creating new rotation. Okay. Again, still AC induction motor. Okay. The rotating magnetic field of the stator drags the rotor around. The rotor does not quite keep up with the rotating magnetic field of the stator. It falls behind or slips as the field rotates. In this animation, for every time the magnetic field rotates, the rotor only makes 3/4 of a turn. If you follow one of the bright green or red rotor teeth with the mouse, you will notice it change color as it falls behind the rotating field. The slip has been greatly exaggerated to enable visualization of this concept. A real induction motor only slips a few percent. Now, you need to have slip in order for the motor to rotate. If you do not have slip, then the motor will simply be stationary. But the synchronous speed and the slip never catches up with each other, because then you will have no motion. Use list of application. Okay. And again, here is your list of applications. I'm not going to do anything on that. That's a matter for yourself to look at. Okay. Thank you for your time. Have a good day. Bye bye. Okay. End stream. End.